First, we discussed about the potential of the continuous charge distribution, and then previous to that, we discussed some problems based on the conservation of energy, right? So now let us see some conservation of energy or potential related problems due to this continuous charge distribution. So then, continuous charge distribution of bodies like a ring or a disk or such a problems, continuous charged objects. And so now here, let us see this one of the problem here. The find the electric field potential at the center of a hemisphere of radius or having the uniform surface charge density sigma. So in the previous classes, actually similar to this, we already calculated the potential field at the center of this hemisphere. And I think in the last examination we solved a problem like 1/4 of the sphere field due to this 1/4 of the sphere at the center. Now similarly, now it's a hemisphere, now hemispherical shell. Now it is having the surface charge density sigma here. Now we need to write this potential at the center. So as we know, when compared to the field calculations, the potential calculations are easy. So potential calculations are easy. So just again our procedure is same. We consider a small element here. So this is the element what we are taking here. So this is the element ring element what we are taking here. So then our ring element, this R is the radius there. I think you got this our ring element here. And so now this small r is the radius what we are taking here. Radius of this ring, and this side we are taking it as x. And now by using this triangle, let us consider this triangle, that you can write small r as r sin theta and this x as r cos theta we can write. Next, let us write the charge present on this ring element here. This is a small ring element. If you cut the hemispherical shell like that, you will get a small ring element. And so now the charge present on this ring element, you can write it as we know the how to let the charge present on the two-dimensional object like a surface charge in terms of surface charge density. So sigma into that area dA term we need to write. And so the dA is nothing but you can write it as 2 pi r sin theta into 2 pi r, actually it is 2 pi r dr, where 2 pi small r into dr we need to write. That means width of this element we need to write. And so now that small r is r sin theta, so 2 pi r sin theta into this width we express in terms of this theta here, d theta. So that we can write as r d theta. So now this dq element, dq charge present on this small element here. Now this ring element, so we can write the potential due to that ring. So actually it is 1 by 4 pi epsilon naught dq by our general formula for the ring is under root of r square plus x square you will get here actually. This small r square plus x square is nothing but this capital R you will get here, and so then we can write this as capital R expression here, right? That's just substitute this dq value here, and then after simplification we will get dv is equal to sigma r by 2 epsilon naught into sin theta d theta. Just we need to integrate this value here. So we need to integrate from 0 to pi by 2, because if you start for example from this top, then theta value will be 0. When you reach this point, then theta value will be pi by 2 you will get. So we need to integrate from 0 to pi by 2 here. Then 0 to pi by 2 means then you will get this value as 1. This is the integration minus cos theta. Just we need to substitute these limits here. Therefore potential at the center is nothing but sigma r by 2 epsilon naught you will get. So that is the potential at the center of a hemispherical shell, right? That's just a similar procedure like what we are doing the previously potential due to the continuous charge distribution. In a similar way we are writing the potential due to a small element, and then we are integrating that. So here that element is in the form of this that element is in the form of a ring. So just we need to apply that ring formula here, right? So next let us say this problem. So now this problem is a circular ring of radius or with a uniform positive charge density lambda per unit length is located in yz plane with its center at the origin. A particle of mass m and a positive charge q is projected from the point root 3 r comma 0 comma 0 on the positive x-axis directly towards the O with initial velocity v. Find the smallest value of v such that the particle does not return to the point P. So here we are projecting the particle from here, and it should not return to this point here. That means it should go away from this. And here the important thing is this ring is carrying this positive charge here, positive charge density, and we are projecting a positive charged particle only, a positive charge small q. And so now first we need to identify in such a problem, such a lot of problems will be there here. The minimum velocity, smallest velocity required here. So in such a problems, what we should first identify is minimum means what is the minimum condition in the given problem. So here if you project the particle up to a particular point, that means if the particle is able to reach up to a particular point, then automatically it can go away from this point here. So that point we need to identify here. So the particle just to reach that point, if once it reaches that point, then automatically it goes to the infinite distance. That means it doesn't return to this, returns to this point P here. So here, just here, if you can observe this, when you are projecting a positive charged particle along this direction with the speed v, automatically there exists some repulsive force between this ring on this point charge here. So because of that repulsive force, that velocity goes on decreasing. Now suppose we are projecting the particle with such a velocity such that just it reaches the point O here. When it just it reaches the point O, then that velocity becomes minimum, because once it crosses the point P here, for example here this object is crossing this point P here, that means point center of this ring here, then automatically because of this repulsive force it will move away from that. So once the particle is, for example here, then the force acting on this particle will be along this direction here, so the repulsive force will be there on this particle here. So once that repulsive force is there, then you can observe this, the particle automatically moves away from that. So our minimum condition is nothing but just to reach this point here. So now that is our minimum velocity required. So just we can apply the procedure is just we can apply the conservation of energy. So here when the particle is at point P, we can conclude that the particle is having some kinetic energy because we are projecting with the velocity v, and it is having that potential energy because these two are nearby. Those two, whenever two charges are nearby, whenever two charges are interacting with each other, definitely the electrostatic potential energy will be there. So at point P, both kinetic energy is there and potential energy is also there. When it reaches the point O, it has only potential energy because we are projecting with the minimum velocity here, and so that just it reaches this point and there it comes to the rest there, then it becomes a minimum velocity. Once it slightly crosses that, then it goes to the infinite there, so that the particle doesn't return this point here. That means the minimum velocity means here we consider that velocity of this particle will be 0 on reaching the center. So when it reaches the center, the only energy is potential energy. There will be some electrostatic potential energy between this ring and this point charge here. So just by applying conservation of energy, you can solve that problem easily. So then just we are writing this expression here. The potential due to this ring, we can write it as lambda r by 2 epsilon naught into, in terms of this lambda we are writing here. Actually that potential due to ring means it's a simple expression only. So that is 1 by 4 pi epsilon naught. If q is the, for example, q is the charge, then q by under root of r square plus r square plus x square we need to write here. Like suppose say r square plus x square at a distance of x from the center. So now here this q value we need to write because here this linear charge density is given. So that linear charge density means we can express this q value as so in terms of this lambda, we can write this q value as q is equal to lambda into 2 pi r. So just if you substitute this expression here, then you will get this expression. This formula you will get. And so there that x is nothing but root 3 r is given. So finally here you will get this potential at that point as lambda by 4 epsilon naught you will get. And we know potential, if you know the potential, then potential energy is nothing but, so at point P, the potential energy we can write it as simply potential at point P into the charge you can write. So potential at point P is nothing but this lambda by 4 epsilon naught. So lambda by 4 epsilon naught into Q. That is nothing but what we are writing here. And the kinetic energy of the particle P is, this is the kinetic energy. Kinetic energy at the point P is half mv square here. So this is a Ke. So kinetic energy, that is. So now the total energy we can write it as total energy at that point is potential energy plus kinetic energy. So when it reaches the center, then it is having only this potential energy will be there. So lambda q by 2 epsilon naught we need to write. That is a potential at the center. Just simply potential at the center means in this expression you need to substitute x is equal to 0. Then 1 by 4 pi epsilon naught q by r you will get. And again same simplification here. Q means 2 pi lambda into 2 pi r we need to write. So then lambda by 2 epsilon naught you will get potential at the center in terms of lambda into this q. And just by simplifying this equation, then we can so just by simplifying this equation, we can write this equation expression for this velocity here. So expression for that velocity is nothing but v is equal to under root of lambda q by 2 epsilon naught into m. So that is the velocity, minimum velocity required there. So just again, this is the conservation of energy problem only. Like previous classes, we discussed some problems based on the conservation of energy, electrostatic potential energy, and problems based on the conservation of energy. So just here also, just the continuous standard distribution is involved here. Just the potential due to the ring is involved here. That is only the difference there. So such a lot of problems will be there based on this minimum velocity calculations. So I will explain first. Let us see such a model problems here. So here let us see one more such a problem here. So now let us see this problem. A unit positive charge of mass m is projected with the velocity v inside the tunnel as shown. The tunnel has the made inside the uniformly charged non-conducting sphere. The minimum velocity with which the point charge should be projected so that it reaches the opposite end of the tunnel is equal to. That means now it is a charged sphere, uniformly charged sphere here. We are projecting a point charge from here. Now this is also a positive charge. This is unit positive charge here. Let it take it as q, and finally may substitute that q value there, right? And so now here it is. We are projecting from this point here so that it reaches this other end. So it reaches this other end in the sense we can consider this as so now it is reaching this other end. It should reach this other end of this tunnel here. So here again we need to consider the minimum condition when the velocity will become minimum, or with the minimum velocity how it can reach the opposite end we need to consider here. With the minimum velocity means just observe this. When you are projecting this particle here, and initially we know this electric field direction will be away from the center. So electric field at any point will be like this, away from the center you may get. And similarly, if you are taking a point this side, it will be away from the center you will get. So this is the direction of this electric field at that point here. And so then at this point, if you consider exactly at this point, if you consider, then field will be along this direction you will get here. So then it will be along this direction here. So just I am representing the electric field directions here. These are the electric field directions at different point. At any point on this radius, it will be along the direction. So this is the direction of this electric field. Similarly, this is the electric field direction here. So now from this, I think you can got this condition easily. So if you are in this half of this tunnel here, first half of this tunnel or left half of this tunnel, then there will be some retarding force will be there on this. Because of this, one component of this field force will be there towards left here, right? And so such a retarding force will be there here. And whereas on this right half of the tunnel, if you consider, that force will become an accelerating, because the component of force due to this electric field will be towards right you will get. So I think now we go, you can understand that easily. I think you got this. What is our minimum condition? So minimum condition is nothing but just it is able to cross this center of the tunnel. If it crosses the center of the tunnel here, if it crosses this point here, if it crosses this point, then automatically because of this repulsive force, it reaches the other end of the tunnel here. So our condition is just we should project the particle here with the minimum velocity such that just it reaches this point here, right? And so then just for that we can use the potential energy conservation, again similar to that our previous calculation. So energy at this point will be again potential energy and kinetic energy will be there, and energy at this point will be potential energy, only potential energy will be there because we are projecting with the minimum velocity. So right, I think you can solve this problem now. And so then like suppose simply here the important thing is potential inside this. When you are writing the potential on the surface means, that means I will write the energy terms so that you can write this, you can do the remaining calculations here. So initial energy I am writing as half mv square plus 1 by 4 pi epsilon naught into q by r, potential energy. Here I am writing in terms of charge here, and later you may convert this into in terms of charge density, because our options are in terms of charge density, because that is given in this data here. This is our initial energy, and final energy we can write this as 0 plus potential at the center into Q. Potential at the center of the tunnel here, this V is. So potential at the center of this is potential at the center of the tunnel. So potential at the center of the tunnel means we need to write our potential inside this uniformly charged sphere formula we need to write. So that potential inside the uniformly charged sphere we can write it as kq by 2r cube into 3r square minus small r square into this is the potential energy, potential term. So potential into this charge we need to write here. So just this small r value is nothing but r by 2, and substitute this and you can equate these two energies there. So here this small r value is nothing but, that means here I can write this as q by 8 pi epsilon naught r cube into q, and this term is nothing but 3r square minus this r is nothing but r by 2, so r square by 4 you will get, and simplify this you will get this initial final energy. Now just by conservation of energy you can write this initial energy is equal to final energy here, right? Just to simplify those two terms, then you will get this minimum velocity required, and finally you need to replace this capital Q in terms of this rho, and a small q value is given as unit. That means the small q value you can substitute 1 here. So then and a capital Q value we can substitute by using in terms of this. So I will write here. So small q value is finally 1 unit 1 coulomb, and this capital Q value we can write it as rho into 4 by 3 pi r cube. So then capital Q value can substitute like this, and then finally you can substitute these values, and then you can calculate this velocity required there. So that is a way to solve this problem, right? I think you can do the remaining calculations. So next let us see some more problems are there similar to this. And so now let us see this problem now. Enlarge this. So a charge Q of uniformly distributed in a spherical volume of radius r, a particle of charge Q and mass m is projected with velocity v0 from its surface of a spherical volume to its center. The minimum value of v0 such that just it reaches the center. Assume that there is no resistance on the particle except the electrostatic force, the electrostatic force of the spherical volume. So that means just it is similar problem only. It is also volume distribution of charge. They are directly asking that the particle just has to reach from center to the surface to the center here. So just I will draw this spherical so just we are projecting this particle here from the surface to the center, right? So suppose say this is the point A, we are projecting from the point A, and this C is the suppose say center of this uniformly charged sphere. So here again our calculation is same only. Just we need to apply the conservation of energy only. That conservation of energy is nothing but you can write this as the conservation of energy, simply we can write it as same as that of our previous calculation. So I can write this initial energy as, so initial energy is equal to half m v square plus 1 by 4 pi epsilon naught into q by capital R, because this is the potential energy on the surface. Just it reaches the center here. So then this is final energy is equal to, final kinetic energy will be 0, and again we need to write the potential at the center. So potential energy at the center. So to write the potential energy at the center, first we should know the potential at the center. So in the previous classes we derived all those expressions. So potential at the center is nothing but 3kq by 2r. It means 3 by 2 times the potential on the surface, you can say. So which I can write it as 3q by 8 pi epsilon naught r. And so again apply the conservation of energy. That means this E initial is equal to E final by conservation of energy. So then you can find the V value here. This velocity expression you can calculate here. So just substitute these terms and simplify this. You will get this energy, velocity required, minimum velocity required. So next let us see another problem based on this. Yeah. So let us see this another problem similar to this. Say semicircular ring of radius 4r and a charge 3q is distributed in such a way that one quarter q is uniformly distributed and another quarter 3q is uniformly distributed. Along its axis, a smooth, non-conducting and uncharged pipe of length 6r is fixed axially as shown. A small ball of mass m and a charge q is thrown from the other end of the pipe. The ball can come out of the pipe if. So here also such a similar problem, right? I think you can understand that easily here. You got this condition, minimum condition. So now this is a semicircular ring. And so here you should identify, you should understand this problem here. In this semicircular ring, one quarter of the ring is having charge q and other quarter is having this charge 2q here. And along this axis there is the radius of this pipe is 6r, and along this axis now there is some pipe here, non-conducting pipe here, and it is uncharged pipe, so a smooth pipe. So along this pipe we are projecting a particle here, so we should project the particle such that just it can reaches the other end, so that minimum velocity they are asking. So while it is coming here, this particle will experience some repulsive force here, right? So just again, if you are projecting the particle, so this side the force acting when the particle is supposed say on this left side of the ring, then the force will be along this direction, right? So when the particle is on the right side, the force will be along this direction. The repulsive force will be along this direction. So now we can easily understand that when the particle is coming towards the center, it experiences some repulsive force. So again, if you that means repulsive force means that force will act as a retarding force. And whereas if the particle is coming along this crosses the center, that force will become the same repulsive force will become an accelerating force. So here the minimum condition is the particle should cross the center. If it is able to cross the center, then automatically it can reaches the other end of the pipe here. So that is our minimum condition. So that velocity at this point should be greater than 0. Simply it is greater than 0 we can consider here, because they are asking in terms of this greater than 0 conditions. So I can write this as so just again I will write those equations, initial energy and final energy, remaining calculation you can do. And so before that we need to write the potential at this point here, potential at this point due to this ring. So that distance we can calculate it as from this ring to this end of this pipe here. So that distance we can write it as this is, now this distance will become 3r and the radius is 4r. So I can easily write this as 5r, this distance, right? So initial potential I am writing here first of all. So initial potential we can write it as k into q by 5r plus k into 2q by 5r, because this total charge will be the either q or 2q, the total charge will be at the same distance. Every element of this one quarter of the ring will be at the same distance from this point here, and so directly we can write this kq by r formula. In the ring we discussed already. And so now that is potential, so you can write the potential energy easily. So now I am writing the total with the help of this. I am writing this initial energy here. So initial energy is nothing but half m u square. That initial energy, initial velocity is given as u, plus this total potential energy we need to write. Potential is I can write it as 3kq by 5r into this charged particle charge is q. So I can write it as into q. So this is into q, right? So this is initial energy. Now the final energy we need to write here. So that final energy is nothing but, so there I am taking some velocity there, or you can consider it as minimum velocity, means it should be 0. The minimum velocity if you are taking, then final kinetic energy should be 0, or it should be slightly greater than 0 actually, right? Or I am taking condition like it is greater than 0, because here this greater, in terms of greater than 0 they are asking here. So I can write this as some velocity v is there, and later I can say this as v is greater than 0. So plus potential at this point. So potential at this point I can write as total 3kq by the radius is 4r into q again. And so now again by conservation of energy you can equate this. Initial energy is equal to final energy, and from this you can simply write this as half mv square value we can write here. You can use this condition as half mv square should be greater than equal to greater than 0, because it should reach the other end of this point means. So simply use this condition here, then you can calculate this v value from this, right? I think you got this. So this is the initial energy expression. This is our initial energy expression, and this is final energy expression, and just we are applying the conservation of energy to get this initial velocity condition. Just now what we are taking is energy at this point, kinetic energy at this point should be slightly greater than 0, so that it can cross that point and we can write this expression here. So that is another problem based on this. So such a type of lot of questions will be there based on this. So we discussed a majority of the models based on the minimum velocity calculations. I think now you got some idea about those problems, right? So just we need to identify that up to where the particle should be projected, so that it can reach the other end of the given problem. Either it may be tunnel or the pipe like this. So you can easily solve such type of problems there. And there is another such a problem here, and is similar to that of previous problem which we solved already. Like just they are asking to penetrate through the sphere. They are asking here. This is exactly same as that of to reach the center. So see this problem. A bullet of mass m and charge q is fired towards a solid uniformly charged sphere of radius r of total charge q. If it strikes the surface of a sphere with the speed u, find the minimum speed so that it can penetrate through the sphere. Neglect the resistance. Penetrate through the sphere means, so here again the minimum condition is, can you guess the minimum condition? Up to what point the particle should reach, the bullet should reach here? It is nothing but exactly at the center, right? So when it reaches when it crosses the center, then again the repulsive force will be there away from the center here. And so because of that repulsive force, automatically it can penetrate through this sphere here. So exactly it should reach this point here. So this problem is same as that of our previous, just to reach the center. So here we discussed one problem just to reach the center here, this problem. So those two are exactly similar only, either to reach the center or to cross the to come out of the sphere, means both are automatically. If it is reaching the center, if it is able to cross the center, then automatically it reaches the other end of this sphere here, right? So those are some problems based on this minimum velocity problems. And so now let us see this now question here, a disk problem, a problem related to disk. So this is a non-conducting disk of radius a and uniform positive charge surface density sigma is placed on the ground with its axis vertical. A particle of mass m and charge p is dropped along the axis of the disk from a height h with a zero initial velocity. The particle has q by m is equal to 4 epsilon naught g by sigma. Find the value of h if the particle just reaches the disk, and sketch the potential energy of the particle as a function of its height. Find its equilibrium position. So actually it's a previous IIT question, advanced question here. So along the axis of a disk we are releasing a particle such that just it reaches the center of the disk. So we need to find this from what height we should reach the particle, and just they are asking variation of the potential energy and its equilibrium position, just they are asking here. So here this this is the actual condition here. So this is the disk here. So along this axis of the disk we are releasing a particle here from a height h. So the given condition is we are releasing from rest here. So the particle just reaches this point here. Just it is able to reach this point here. Just it is able to reach this point means again you can understand that the particle will come to the rest at this point. Because of why it comes to the rest at this point means because of a repulsive force from the disk. Because disk is having the positive charge and here we are releasing the positive charge only. And so both are like charges only. So because of that there is some repulsive force between them. And so because of that repulsive force, the particle will reaches the center of the disk with the zero velocity there. And so now here just I am writing this potential at a distance of h. So potential at this point first we are writing, because to write the energy conservation of energy we need to write the potentials. So I think from these calculations or from these problems we understand that whenever you are writing the potential energy, so we need to know the potential at that point expression. So potential at that point expression is known to us, then potential into that charge we can write. Wherever the charge we are placing, whatever the charge we are placing, that charge we can write here. So potential at that point we need to write. Now potential at a distance of h. This is the potential due to the disk formula. Potential due to the disk at a distance x from its at a distance x on its axis formula. So sigma by 2 pi epsilon naught into under root of a square plus x square minus x. So here this the x is nothing but this h is given. So h square instead of x just we need to write h. This is the initial potential. So now potential energy means into small q we can write simply. Now final potential means potential on the center, right? So potential on the center means in this expression you can substitute this x is equal to 0, then sigma a by 2 epsilon naught you will get here. So now that is the potential here. Now let us substitute those values in our conservation of energy equation. So now the conservation of energy equation I am writing here. So initially it is having that potential energy. So initially it is having some potential energy. So now that potential energy is nothing but mgh. So that should be equal to change in this electrostatic potential energy here. Here initial kinetic energy is 0, final kinetic energy is also 0. Or you can also write this equation as, you can also write the same equation like this. Initial energy is equal to final energy you can write. So initial energy is nothing but, you can write this as mgh, gravitational potential energy will be there. So then Vh, potential at a distance V initial, or we are mentioning that as Vh, V of h into Q. This is equal to final potential energy is, gravitational potential energy is 0 and electrostatic potential is V of V naught into Q. This is potential at the center. Then potential at this at a height h and potential at this point O, we can substitute those values, or here what they are writing here is mgh is equal to, we can write this value as q into, so q of potential at the center of the disk minus potential at a height h from this center. So now that equation directly they are writing here, so we can also write it by our general way like this, and just substitute those values here, v naught and vq values. So then, and the given expression is sigma by, one relation is mentioned in our problem here. So sigma by 2 epsilon naught is equal to 2 mg. You can use that value here, you can substitute that value here. So this mg will be cancelled on both sides. So you will get an equation in terms of h like this, and on simplifying this h equation you will get 4a by 3. That means if you release the particle from a height of 4a by 3 along its axis directly above the center of the disk, then that particle will reaches the center of the disk with the zero velocity. We are dropping the particle from the rest and again it reaches the center of the disk with the zero velocity there, right? So that is first part of the problem. So we calculated the height required, from what height we need to release the particle. And next let us see, we need to draw the variation of its potential energy of the particle. So the variation of potential energy of the particle means here they are not asking either electrostatic potential energy or the gravitational potential energy separately. Potential energy of the particle they are asking here. So potential energy of the particle means both the gravitational potential energy as well as electrostatic potential energy we need to write here. Suppose we are taking this condition like when it is at a height x above the center, then gravitational potential energy is mgx and electrostatic potential energy is q into v of x, where v of x is nothing but potential at that point, direct formula only that one. So then we are replacing this value here, this sigma by 2 epsilon naught. So we can write this, instead of this sigma by 2 epsilon naught 2 mg we can write here. So this is actually, it is not plus, it is into. So 2 mg into under root of this value you will get. And on simplifying this equation, now you will get this expression like this. That mg I am taking common, so that you will get an expression like this. And now we need to identify this variation here. So this is a variation of this potential with this. Now to identify the equilibrium position. So to identify the equilibrium position, at equilibrium we know this potential this dx by du by dx value should be equal to 0. Our equilibrium condition is nothing but, at equilibrium we can write it as f is equal to 0, right? And we know the relation between f and u. So f is equal to minus du by dx. So this value is equal to 0. And so you can write this as du by dx is equal to 0. So that is nothing but the condition what we are using here. Du by dx is equal to 0 we are using directly at equilibrium. So then just to simplify this equation now, you will get the a is equal to x is equal to a by root 3 you will get. And to represent these values here, you can substitute this x is equal to a by root 3 in this equation, then you will get this least potential energy you will get here. So least potential energy you can calculate by using this. And initial potential energy is nothing but when you substitute this h value which we calculated previously, that means x is equal to capital H we need to substitute. That is nothing but when this x is equal to h is equal to 4a by 3, then you will get the potential energy here. And when it is at the equilibrium position, if you want to calculate which is the minimum potential energy, you can substitute this a value in this above equation, then you will get this minimum potential energy here, that is root 3 mga. So that is a variation of this potential energy with the distance here. So from this equation we can draw this graph here, we can identify this variation here. So it is a potential energy variation, right? And next let us see some problems based on this work done calculations here and potential calculations. And this is a simple problem here. I think all of you can solve this easily. Now say this problem: a conducting bubble of radius or radius A and thickness T is very much less than that of A, has a potential V. Now the bubble is collapsed into the droplet and then electric potential on its surface is, right? I think all of you can solve this problem. So it's a conducting bubble of radius A and thickness T is having some potential V here. So just we can write the potential expressions there. The potential expression we can write it as, for that it is nothing but our spherical shell you can write here. Therefore V is equal to, I can write this as so it is kq by A we can write. So there is a potential of this drop. Now it is converting into a droplet. That means it is collapsing, that bubble is collapsing, then it is converting here. So let's suppose this is equation 1. So this is our equation 1, initial equation. Now we can write this as, when it is collapsing, just we need to find the radius of this drop here. So to find the radius of the drop, just we are equating this volume. So volume of this bubble is equal to volume of this drop here. So that implies we can write this volume of this bubble as 4 pi a square. This is surface area into thickness. The T is the thickness is given there. And this is equal to the volume of the drop we need to write. That is 4 by 3 pi r cube we can write here. And so you can simplify this. That 4 pi you can cancel, and from this r cube is equal to, this r cube value I can write as 3a square t by t. That 4 pi you can cancel on both sides. Therefore from this I can write this r is equal to 3a square t whole power 1 by 3. So that is our radius. Now the charge remains same. Charge is conserved here, so charge will remain same. Now the potential of this drop we can write as, the potential of the drop we can write as k into q by r we can write. That r means we need to substitute that value here. Therefore I can write this as potential of this drop as kq by 3a square t whole power 1 by 3. Now we need to convert this in terms of this V. To convert this in terms of E, we need to write A outside here. So just I am multiplying with A and dividing with A here. So then here I am multiplying with A and dividing with A. Now kq by A is nothing but our potential on this drop here. So therefore this is into, this is V into, you can write this as this A also I am writing inside here. This is not Q, this is A, right? And so now this value we can write this as you can simplify this equation. Now we can write this A also inside here. So when I am writing that A also inside, I can write that as A cube by 3A square into T whole power 1 by 3 we can write simply. So which is nothing but V into, I can write this as A by 3T whole power 1 by 3 we can write here. So now that is the potential of this drop when it is converting into drop here. It's a simple problem only. And next, so let us see some other problems based on this here. So now this is simple again potential calculation here. I think all of you can solve this problem also easily. So now here the following diagram represents the semicircular wire of linear charge density lambda is equal to lambda naught sine theta, where lambda naught is a positive constant. Then electric potential at point O. This O is nothing but the center here. This is the point O here. So at this point we need to calculate the potential. So just we consider a small element here and we write the potential due to that small element. So here I am taking this as a small element here. So this is our small element. So this is our d theta you can consider here. So then potential due to that small element you can write it as this is our d theta term. So potential due to that small element you can write as that charge on the small element is nothing but lambda into dl, length of this element. That lambda is nothing but given by this expression lambda naught into sine theta into that dl is nothing but this dl you can write as r d theta. Now potential due to this small element we can write as 1 by 4 pi epsilon naught into dq by r. This dq is nothing but lambda naught into r sine theta into d theta by r. This will be cancelled and we need to write this value here sine theta d theta. Now these limits are from minus pi by 2 to plus pi by 2 because we need to integrate from here from this side and this side also we need to integrate. So this is from minus pi by 2 to plus pi by 2 so that you will get the total semicircular ring you can calculate there. And so that results as 0. So then potential at this point will be 0 you will get here. Potential at this center of the ring you will get that value as 0, right? And so simply here you can observe this potential on this one side of this ring will be positive charge density you will get and potential on this other side will be negative charge density you will get here. In general if you are taking this theta is important here. This theta is taken with the vertical. If theta is taken with the horizontal then it will be different. This theta they are defining, we are not taking here, we are not taking this theta value, they are defining in this problem here, they are taking this theta, they are defining this theta as with the vertical they are defining here. And so that according to that only we need to consider here. For example in the same problem if it is given as theta with this x-axis then total positive charge only you will get. Total positive charge means then you can integrate accordingly here according to that given conditions there. Then theta limits will varies from 0 to pi you will get. So here you will get 2 you will get. So that is that problem potential calculations there. And next let us see this problem here. In the adjoining figure represents a semicircular loop of radius r and loop of charge q and radius r. The minimum velocity with which a point mass m is to be m of charge q minus q is to be projected from the center of this semicircular loop so that it becomes free from the influence of this loop. So it's interesting question only. It is a combination of like electrostatics and the gravitation. Just what they are asking is it is becoming free from the influence of ring means just they are asking that escape velocity. When you are projecting a particle from the center it should escape from this influence of this ring. So that means here we are not considering the gravity here. It's a gravity free space let us consider. So that means from the influence of this ring only the force between them will be this electrostatic force only. And so simply we know how to calculate the escape velocity there. So all the escape velocity calculations are also based on conservation of energy only. So then conservation of energy means initial energy in this case also now initial energy is nothing but when it is at this point. So initially it is having both potential energy due to this ring and a kinetic energy will be there. When it is escaping to the infinity, at infinity we know that both potential energy at infinity potential energy is 0 and we are projecting with the minimum velocity, so that kinetic energy also becomes 0 here. So just again by using conservation of energy we can write here like so this by conservation of energy we can write as, so initial energy is equal to final energy, right? So now initial energy is nothing but initial potential energy we need to write. So potential energy, I can initial kinetic energy first I am writing as half m v square, and initial potential energy we need to write. Initial potential energy is nothing but potential due to that ring is kq by r, capital R, into that particle charge is negative, so that this potential energy is negative here. That's what I am writing negative sign here. This is equal to final kinetic energy is 0 because we are projecting with the minimum velocity, plus final potential energy is also 0 because it is going to the infinite distance from the semicircular ring. And so just to simplify this, then you will get this velocity here. So I can write this half m v square. So half m v square is equal to q into q by 4 pi epsilon naught r, and therefore this v is equal to, you can write this v expression as sorry, this 2 is cancelled here, you can cancel that 2. So I can write this as q into q by 2 pi epsilon naught into m into r. So that is the velocity required at this point there. So then that is our option. That means you will get this option C. This is the correct option for that question. So like that is a conservation of energy application. That means escape velocity calculations here. Now as we come to the gravitation, let us see this another problem similar to that. And actually this type of problems we solved previously in the conservation of energy due to the point charge distribution. Now exactly a same problem, just only this potential due to the solid sphere we need to this sphere we need to write here. So now let us see this problem now. A particle of mass 1 kg and a charge 1 by 3 microcoulomb is projected towards a non-conducting fixed spherical shell having the same same charge uniformly distributed on its surface. Find the minimum initial velocity of the projection required in the particle just if the particle just grazes the shell. So that means we are projecting this particle from infinity here. The particle just grazes the surface here. It travels along the surface here. So that is a given information there. And so it grazes along the surface means we solve such a problems there. In the previous, in case of point charges, we solve that problem. Now here in case of the spherical shell and the point charge, we need to solve this problem here. Exactly same as that of our previous calculations. And so just to see here, just first I am applying the conservation of energy here. It is coming like this. And it is just grazing the surface here. So it grazes the surface means it travels like this. So the velocity of the particle will be, let's suppose velocity of the particle at this point is v. Initially let us take it as the particle is so then in minimum initial velocity they are asking here. So this initial velocity I am taking it as some u. So just first apply the conservation of angular momentum. So first I am writing this by conservation of angular momentum. So initial angular momentum is equal to final angular momentum. Now that initial angular momentum we can write as m into u into, this will be the perpendicular distance. So 0.5 mm. So I am taking it as 5 into 10 power minus 3. So minus 4 you will get because I am taking it as 5. So I can write this as 5 into 10 power minus 4 meters. And this value is equal to, you can write this as final angular momentum, we can write it as when it is just grazing the surface here. When it is grazing the surface, you can write this expression as m into v into r. Now r is nothing but radius here, so I can write this as 10 power minus 3. 1 mm is given that radius, so 10 power minus 3 we can write here, right? And so now this relation v is equal to, I can write this expression as v is equal to u by 2 we can write here. Basing on this 10 power minus 3 you can cancel here, so 0.5 you will get. At 0.5 is nothing but u by 2. So this is our equation 1. And now just apply the conservation of energy again. So after this, so by conservation of energy, So by conservation of energy, we can write as initial energy is equal to final energy, we can write here. So that initial energy is nothing but initial energy is it is projected from infinity. So only it is having this initial kinetic energy here. Potential energy will be 0. And finally, suppose it is having this potential energy and kinetic energy. So kinetic energy is half mv square, and potential energy you can write as k into q by r. We can write potential on the surface of the shell into this charge. And so then this equation, this u value you can substitute, this v value is u by 2, you can substitute and simplify here. So half m u square I am taking common, then you will get 1 minus 1 by 4 you will get. So this is equal to, this is 4. So this is equal to, you can write this as q into q by 4 pi epsilon naught r, we can write here. So this is our equation, and by simplifying this we can write an expression for this u, and here these values are given here, that small q and capital Q values are given. You can substitute those values there. So that means small q and capital Q both are same only. It is 1 by 3 microcoulomb, and mass m is given as 1 kg and r is 1 mm is given. So substitute those values, then you can calculate these v expressions there. So this is same as that of our previously solved problems. The only difference is there both the charges are point charges only. Here one spherical object, spherical shell, and the point object is given. So just the potential due to that spherical shell we need to write here. That's only the difference there. So simplify this and find the u value. So next let us see some work done problems here. Let us see this problem now. So let us see this question. An arc AB of with the center C and the infinitely long wire having this linear charge density lambda were lying in the same plane. Minimum amount of work done in moving a point charge q naught from A to B through the circular path AB of the radius A is equal to. That means now here they are moving a charged particle from here to here, right? And so now here electric field is, the direction of electric field due to this will be along this, because it's infinitely long. I will represent this direction here. The direction of electric field will be along this line here. So the direction of electric field due to this wire will be away from that wire, you can say. So this is the direction of this electric field here, right? And so from this what we can conclude is this B and C will be normal to this electric field. They are normal to the electric field means they are at the same potential, you can say. B and C will be equipotential, we can conclude here, right? So when B and C are equipotential, the work done in displacing the particle from either A to B or A to C, both are equal only, because this the work done by this electrostatic force is independent of path followed. It only depends on initial and final potentials here. So then we concluded just now this potential of A and B are equal, right? Because equipotential surface is perpendicular to this electric field here. We already concluded this equipotential surface means due to line of charge, actually such identical potential surfaces will be cylindrical surface you will get. So B and C will lies on such a same cylindrical surfaces, so that we can conclude that B and C are equipotential. So work done in moving the charge from either A to B or from A to C, both are same only, right? So just we calculate the work done from this A to C, and just we know we need to write the potential difference there. So potential difference due to this line of charge we need to write here. So we know already potential due to this line of charge. So potential due to line of charge expression, and then that equation we need to write here. So work done we need to write this as so work done in displacing the particle from A to B is equal to work done in displacing the particle from A to C. Since the reason is potential at B is equal to potential at C. Both are equipotential surfaces there. And so now work done along this AC, we can write it as final potential minus initial potential into this charge we need to write here. This potential difference we need to write here. So that potential difference means we already derived that potential difference formula for this line of charge here. So potential, the difference is nothing but lambda by 2 pi epsilon naught into ln. It is r by r2 by r1 you will get. So which is nothing but 3a by a 2a you can write here. Into the charge is given as actually q naught. We are displacing the charge q naught here. And therefore it is nothing but lambda by 2 pi epsilon naught into, this will be ln, this is into q naught I am writing here, q naught into ln 3 by 2 we can write here. So this is the work done in displacing the charged particle from this A to C. So this is our potential difference formula I am writing here, potential difference due to this. So lambda by, this is lambda by 2 pi epsilon naught into ln r by r naught or r2 by r1 we can write here. And here simply we are writing like 3a by 2a. Simply you can observe this. First of all, here you need to identify whether it is r1 by r2 or r2 by r1 means that depends on these points here. And you can easily identify here when you are drawing, when you are displacing the particle from A to C. Electric force is acting like this. And so now we need to apply the external force should be towards this wire. Towards the wire means it is in the direction of displacement only. So work done by the external agent should be positive. So work done by the external agent is positive means then here this value we need to write it as 3a by 2a we need to write here. So this is lambda q by 2a by epsilon naught into ln 3 by 2 we can write here. So that is this work done problem. Now such a one more problem is here. I will explain this. Let us say this one. So between two infinitely long wires having this linear charge densities lambda and minus lambda, there are 2 points A and B as shown in the figure. So work done by the electric field in moving the charge from A to electric charge Q naught from A to B is. So now let us see this problem. The particle is to be displaced from this point A to B here. So that is our required condition. So here both the two linear charge densities are there. So potential due to line of charge if you want to write, then potential due to both the wires we need to consider here. So instead of that, what I am doing is I am taking the electric field here. So you can take the electric field. So force into displacement method I am writing here. You may write the potential for this wire and the potential for this wire. So at this point A, if you are writing for example, then potential due to both the wires we need to write here. So instead of that, what I am taking is, that will be somewhat confusing here because one is positive and the other is negative. So instead of this, what I am taking is, suppose here I am taking it is at a distance of x from this. In between this, I am taking one point here. So it is at a distance of x from this wire here, for example. Then this distance I am taking it as x. Then this distance will be, the remaining distance will be, this distance will be, you can write this as 3a minus x you can write here. So at such a point, just I am writing the field. The electric field will be lambda by 2 pi epsilon naught into one is x plus, and due to another is lambda by 2 pi epsilon naught into 3a minus x. So both are along these directions here. So both are along these directions means then both are in the same directions, that we are what we are adding here. Why we are adding this? Electric field due to this away from this wire, and electric field due to this negatively charged wire will be towards this wire. So I can write this as electric field expression as lambda by 2 pi epsilon naught, you can take common. And so this expression you can write as 1 by x plus 1 by 3a minus x here. And now this force will be there in the direction of this displacement here. That means we are applying this force. This force will be, electric force will be along this direction. The electric force is acting like this. EQ will be along this direction. And displacement of the particle is also in the same direction. And therefore I can write this work done is equal to EQ into dx we can write here. And so that is nothing but lambda into q naught by, this is q naught, this 2 pi epsilon naught I am taking common here, then integral of 1 by x plus 1 by 3a minus x dx, right? Now x varies from, that means we are displacing the particle from a to b. So x varies from a to 2a. So just integrate those values and substitute these limits. Then you will get this work done here. Do that calculation. So you will get this expression as lambda q naught by pi epsilon naught into. So this is nothing but you will get this expression as, you can integrate this expression, ln you will get ln 2a by a we need to write, and similarly here you need to substitute those values here. So finally I can write this as lambda by pi epsilon naught into, and then you will get that expression as ln 2 you will get, ln 2 into 2 you will get, so that one 2 will be cancelled here. So just to integrate and substitute those limits there. And such a one more work done question will be there, so I will explain that. Yeah, this one. So let us see this question now. So in the diagram, three infinitely uniformly line of charges are placed here in xy, that means placed on the xy z axis. The work done in moving the unit positive charge from 1 comma 1 comma 1 to 0 comma 1 comma 1. So that means now here the particle is initially say somewhere in the space here. The particle is say initially here in the space. Now it is displacing through this yz plane here, because here x is equal to 0. So then x is equal to, that means the particle is moving parallel to the x axis, right? Initially it is in this space here, like here somewhere here. Now it is moving towards this, that means it is moving along this yz plane. So particle is displacing parallel to the x axis, that we should observe from these points here, the given points. So now they are asking this work done here. So then from this what I can conclude is work done because of this where line of charge along the x-axis will be 0. I think you got this. Why the electric field is 0 means, if you are taking this, if you are displacing the particle, suppose our line of charge is like this. This is our line of charge having some positive charge here. Now we are displacing the point from one point to another point like this. Suppose here this is point A and point B here. This is the line of charge having some charge density. Let us consider infinite line of charge. Now if I displace the particle from A to B like this, if the particle is displaced from A to B, for example like this, then here potential at A and potential at B will be same only, and so you can conclude that work done along this path will be 0 only. Because, or simply you can say this, electric field at this point will be along this direction, electric field at any point will be along this direction only. So displacement and this force are perpendicular, EQ along like this and EQ is along like this, but displacement is along this perpendicular to this EQ value, and so that you can conclude that work done will be 0. And because of this, when the particle is displacing from this 1 comma 1 comma 1 to 0 comma 1 comma 1, I can conclude that work done due to this line of charge along the x-axis will be 0. So only we need to write about work done along this point here, 1 comma 1 comma 1 along the z, y and z planes we need to write here. And for both of them the identical only, the situation will be identical only. And so due to that one of this wire I will write here, and you can multiply with this due to this one of the you can write here, because lambda so different here, so we need to write them separately only. If identical they are, then we can calculate due to one of this and we can multiply with this 2 here. So I am taking this so this work done is nothing but I can write work done because of this line of charge along the x-axis, y-axis, and work done along this z-axis we can write here. And therefore I can write this expression as work done along this x-axis, same as that of our previous calculations. So it is 3 lambda by 2 pi epsilon naught into, this is q, q into, this is this distance we can write it as that r2 by ln r2 by r1 we need to write. Ln r2 by r1 is nothing but we are traveling from this 1 comma 1 comma 1 to this 0 comma 1 comma 1. And so then this value is nothing but ln the distance is nothing but initially when it is at this point the distance from the either x-axis y-axis or z-axis will be equal to root 2 you will get. So it is root 2 by 1, because when it is reaching to this point the distance will become 1 meter only, the distance from either x-axis or y-axis. So this is our r2 by ln r2 by r1 formula. And similarly due to this z-axis it will be lambda into q by 2 pi epsilon naught into this ln value will be same. So ln root 2 by 1 we can write here. For this also the distances will be same only. And this charge is given as work done in moving the unit positive charge. So small q value is 1 and 3 lambda by 2 pi epsilon naught plus lambda by 2 pi epsilon naught. So you will get this value as lambda by epsilon naught. So I can write this value as 2 lambda into q by pi epsilon naught into ln root 2. And ln root 2 means we can write this value here whole square. So I can write this value as finally this is lambda by pi epsilon naught into ln 2 we can write here. So this is the work done here. Because this small q value I am substituting it as 2. So like that you can solve the problems based on this easily. So these are some of the important problems based on this, and practice the remaining problems. I will note those questions. As I said, I'll leave the problems based on the combination of concentric shells, and about the concentric shells and individual problems we discuss after the completion of the Gauss law here. Gauss law. So here simply solve the problems like this, depending on the work done or the potential due to the different configurations, and velocity, minimum velocity problem, that means conservation of energy, work done, or the potential calculations at the different points there. So try to complete those problems. I will give the question numbers based on this, so you have to complete those. So leave the problems based on the spherical shells, that means combination of shells, concentric shells, and earthing of the conductors or the individual charges problems. We discuss all those problems in the next week, that means after the completion of the Gauss law. So complete the problems based on these topics, conservation of energy topics. Thank you.